Let's take a look at some of the fixture configurations that you might consider. First of all, there's the common plate configuration where, as you can see here, we have a supporting plate that is attached to a machine table of some kind, and then we build up the fixture from that plate. So we've got a set of clamps and locators. Here we see some locators used to locate specific surfaces, and then we have some clamping devices that attach those to the plate as well as provide a clamping force. Quite common configuration because it's easily changed and reconfigured. Nesting configuration is also quite common, and usually you see it in the context of a vise jaw configuration. Here the jaws are going to be created custom for the workpiece. As you can see here, we create the complement of the geometry that we are nesting, and we don't have to enclose the entire geometry. So we have both locating surfaces as well as a clamping force applied in both cases, and it's fairly inexpensive, so that's why it's quite popular and very flexible in terms of creating new sets of jaws for different part geometries. If you have been in the lab for 248, you recognize the chick jaw configuration here, where we actually have two positions and a different set of jaws in each position. Again, these are nesting configurations, and we can use both of them, place parts in different stages in each location, and then end up with the proper surfaces being located. If we look at that from the top, what we see are different possibilities for nesting. Here we have the V-block that we talked about last time, and we have different sizes for the V-block and different depths. So if we had a cylindrical feature, we could use the V's here to locate that axis. Don't forget about the process direction and the potential for deviation in terms of how far we are from that vertex. We also have locating surfaces here, here, and here. Usually you have this two-position configuration when you want to have different widths to accommodate different sizes of parts and different nesting geometries that you need to enclose surfaces. An indexing fixture is quite common. Here what we see are three fixtures, all exactly alike, and we're going to place them on an indexing table that rotates. So you can see what's going to happen here. I have a load-unload where the part is placed in the fixture, so this is where my setup occurs. And then we're going to rotate to the next position where a process is performed, and then we rotate again to the next position. So essentially what we have is a part on each of the fixtures that is going through the set of processes. Now you can see the advantage of this, and it has to do with cycle time. The lead time is not affected because, again, the part is going to have to be set up, go through process 1, go through process 2, and then removed from the fixture. So the total lead time to go through all of these processes is still the same. The nice thing, though, is we're going to share a setup between process 1 and process 2, so that we only have to set up once for each of those processes. So we've reduced the setup time, which again is the goal to minimize setup. And the cycle time, again, will be affected by the bottleneck, the longest cycle time here. So instead of performing process 1 and 2 together, we've split them, and therefore the cycle time has been reduced. The downside here is it's going to require 3 fixtures. So the tooling cost has gone up, but we've seen improvements in cycle time and setup time, so there is a trade-off here. The question is it worth the trade-off? Of course, you can have as many positions as is physically possible on this indexing table. And so if we wanted to add additional stations, we might have to increase the size of the indexing table. We can also use a multi-workpiece fixture configuration. At first glance, it might look similar. The difference here is that we're only going to have one process. And here we have two parts. We're going to rotate a part into the process, and then the cycle time occurs, so that one of the parts, one location, is essentially your setup and unload station, where the other location would be the actual process is taking place. The indexing plunger is used to lock it in place. So we'll rotate it into the process, then rotate it out. What is the advantage of this type of fixture configuration? Well, as you can see, we're doing the setup and unload at the same time that we're doing the process on that particular part, and therefore the impact is on cycle time. Note that we haven't reduced setup time as in the previous configuration. We still have the same lead time to get through the process because we still have to go through the setup and unload as well as the process itself. So the advantage here is on cycle time. If you need to reduce your cycle time, this would be one alternative to consider. When we are thinking of a specific fixture configuration and the clamping forces that are going to be involved, or tooling forces as well, we have to consider supports. So in any of these fixture configurations, if I've got a workpiece, for instance, this one is fairly obvious. If we apply a force out here, you're going to create a moment, and that workpiece is going to want to rotate about a point here and obviously go into the plate. So what we need here are supports that will prevent deflection of the workpiece, so that if forces are being applied in this region here, we can still maintain the location and orientation of the workpiece with respect to the process. So this includes both clamping and tool forces. So you have to think about your tool path. Where's the tool going to travel, and what types of forces are being applied, and where do we need to support the workpiece so that deflections do not occur. When we go back to our datums and datum targets, if you recall, it's often the case that the datum targets are used to identify fixturing points, locating points, as well as tooling points. So we can use those points to actually design our fixtures, and it's going to be particularly important when we're dealing with weldments, forgings, and castings, which often go through a secondary process in order to achieve the final geometry. So if you recall, we identified on the design spec specific locations. In this case, we have points on different surfaces of the part, and those are used to create our datum reference frame. Well, what does that look like on an actual part? Here we have an example of spindles that are created through a steel casting process for mining trucks. So we've got our wheel spindles, and the foundry, after producing the casting, is going to perform this rough machining operation, this secondary operation, to provide an axial location, essentially to be able to locate the axis on a machine surface. This helps to reduce locating time when it goes to the manufacturer that the foundry is supplying. And then there's some finishing machining that is performed in-house at the manufacturer. Here's an example of what it looks like after the rough machining. You can note the axis that is trying to be created here. The axis is running down in this direction, and the entire casting has to be machined in order to provide that type of a locating system. When you look at locators, especially for casting, it's often the case that you can design the pattern, as you can see here, in a pattern shop that's being created to produce the mold. So here we have 1/2 of the mold, or the pattern used to create the mold. And in that we can add protrusions as well as pockets that are going to allow us to provide some type of location, because when we have our casting that comes out of the mold, it will need to be located with respect to our machine in order to perform the rough machining. We can also create locators actually on the surface by creating a datum feature with that rough machining. The purpose of clamping is to hold the workpiece against the locators. That is the primary purpose. So when you think of clamping, we're not just concerned about keeping the workpiece from moving, but we're also concerned about it lifting or repositioning with respect to those locators. So we want to maintain the position and orientation with respect to these locators. Of course, also prevent the shifting of the workpiece, and at the same time you have to consider the material that the workpiece is made from, because that's going to affect the amount of clamping force that can be applied. At the same time, you need to minimize handling time for load and unload, because that's part of your setup and it's non-value adding. So if you have lots of clamps, it can increase the setup time significantly. When you add a clamp, you have to be concerned about the location of the clamp. So you can think about the supports on your fixture. For instance, here we have locators, 3 locating pins. And when we're thinking about clamping into the slide here, we want to draw a polygon, the smallest polygon around our locators, and then place our clamps in that region. So you can see here it makes sense to put a clamp either in this location, or this location. Now you may need multiple clamps depending upon what the forces are. But ideally, if you can get away with just one clamp, then you're going to decrease your setup time. You want to minimize the surface contact area, and the reason for that is tool accessibility to the features that you're trying to create. But at the same time, if you minimize surface contact area in order to increase the pressure, you're going to have to increase the force, and you have the potential for damaging the surface. By damaging, we mean plastic deformation. Don't forget accessibility. You don't want to be placing clamps in the region where the process occurs. So these are typical knobs that are used in clamping, where we apply force to a plate, and in the process of applying that force, we are clamping against locators. Again, as you can see, these are threaded knobs, and so there's going to have to be a corresponding threaded hole in order to get the clamping force. Strap clamp is a very common configuration because it helps us to minimize the surface area that we're contacting, and it's based on the lever principle, as you can see. What we're going to do with a strap clamp is have a small surface region on the edge of the part, and at the nose of the strap we come in contact with the surface. Then we have a pivot here, which essentially is an offset from the plate, and place our strap across that, and then we have a stud that's threaded into the plate, and then a corresponding nut that we tighten on that stud. And then we tighten it using a torque wrench so that we can have a consistent clamping force based upon the torque and the size of the thread. We can adjust our clamping force, and these are just examples of the amount of clamping force that we can attain, and as you can see, it can be quite significant. Again, here you would be concerned about deformation of your workpiece and potentially deformation of the stud itself, because that would affect your fixture. Cam action clamp is very nice for quick setups. As you can see, the arm here can be rotated such that we can easily tighten and release our clamping surface here. Again, you're clamping against locators. So the force on the surface will increase as this cam, and hopefully you've seen the geometry of cam, it's essentially an oval egg shape, so that the radius is constantly changing, and as it gets larger with respect to this surface, then obviously we're moving further, and therefore our clamping force is going to increase. The problem here is that you're going to get an inconsistent force applied by the operator. Each operator and each workpiece will see a slightly different force applied. It can also be susceptible to loosening if significant vibrations are present in the process. So again, you're faced with trade-offs to decrease setup time versus having a consistent force applied. Another common type of clamp configuration, two linkages, and we have a pivot point, as you can see here. That pivot is going to lengthen the overall dimension here, which is providing, as you can see here, the clamping force. When the linkages are aligned, the force is going to be applied. The direction, of course, changes depending upon the actual configuration, and there are many different configurations for these toggle clamps. So we would attach our clamp to our fixture and then apply our force to the lever here to get the toggling effect. Now, as you can see here with a toggle clamp, typically they are low force applications. You'll find these quite often used in welding. So where we have weldments, we could have a lot of toggle clamps that are trying to hold our workpiece up against locators. And then we have our adjustable clamping surfaces that we talked about for the nesting configurations. Here we're going to have a vise clamp with flat locators or V-blocks machined into those surfaces. And with the nesting configuration, we can create custom surfaces that we're clamping against. And all we do here is essentially rotate until we come in contact with our surface and hold it against our locating surface. Note that the only force in this direction, normal to the axis here, is a frictional force. And if you recall from a frictional force, that is not the best way to overcome a tooling force. Also note, your workpiece can pop up because, again, in this direction, in the Z direction, we also just have a frictional force. So there is a downside of using this type of an approach. Well, with the turning center, you're going to see chucks used. Here we have an adjustable chuck so that we can place our bar stock in center here and then tighten up against those surfaces. Note, unless you put notches into your workpiece, again, you're dealing with frictional forces as this chuck is rotating in our turning center. We're trying to prevent slippage of the bar stock or the workpiece inside of the chuck based upon frictional forces, unless you create actual tooling points in there that we could tighten up the chuck against and then not rely just on frictional forces. What kinds of problems can occur in fixturing? Well, you can have debris that builds up over time, especially if we're dealing with material removal processes. So we can have chips and all kinds of material build up in different parts of our fixture, and they may not be noticed. Therefore, we need to keep our fixtures clean after every operation. Over time, our fixtures will wear as we would expect, and therefore we have to qualify our fixtures to make sure that the locating surfaces have not changed significantly. Well, we have surface errors, of course, that are going to contribute to our process capability, and we have work holder errors when setup occurs. So when we place the workpiece in the fixture, each time it will be a unique position. Even though we have our locators, the operator will not be able to consistently locate the workpiece. So again, this is going to contribute to our process capability as well. Your setups for the fixture itself, it could be a modular fixture that we have to build up. It could be a permanent fixture. And then it may require qualification to make sure that the fixture is still locating and orienting our workpiece surfaces correctly. Then we have to set up the workpiece in the fixture, and that will involve clamping against our locators. And then finally, when we place it on the machine table, we're going to have to consider datum referencing in terms of touching off on different points so that we can set up the machine so it knows where our coordinate systems are, as we saw with CNC programming. The other consideration that you have to take into account is the fact that your workpiece geometry is evolving over time. And so as it evolves, different surfaces become available for locating and clamping. So you want to understand at the various stages in your process which surfaces should come in contact with the fixture. Again, we go back to our datums, and we would prefer to use those if they are available. If they aren't available, we need to create those before the features, or at the same time, in the same setup, before the features that are referencing those datums are created. Don't forget, in order to accommodate this change in geometry, we're going to have to consider accessibility of the tool during that process. Also, what are the possible tool orientations based upon your machine configuration? Is it a 3-axis vertical mill? Is it a 5-axis? That will affect your ability to orient the tool. And then finally, the tool geometry can affect your fixture design because you have to accommodate different tools in the carousel that may be used during that process. So, select a fixture configuration that is going to be suitable. Again, there are trade-offs involved, as we've already seen. So if your concern is setup time, reduction in setup time, you may go with a different fixture configuration than if your concern is primarily the tooling cost. And then select clamping that will provide the necessary force to keep your workpiece up against the locators. And finally, don't forget supports. We need to be supporting areas that can be deflected so that we don't lose the repeatability of our orientation and positioning. Fixture configuration, as you saw in the examples, will affect the cycle time. And sufficient supports need to be provided in your clamping region. So wherever you're applying those forces against your locators, make sure that it's well supported. Your clamping devices that you're going to use, you have to plan for the expected forces that could be applied to the workpiece from a tooling perspective.